Morning. Hello. Morning.
Morning. Hello.
Hey. Good. Okay.
Hello.
Start proving those. I think that's where we were, right? See what you can do with those. There are auxiliary segments you're going to need. I think more than one, each one.
I think we did this one.
We did the angles. I think we stopped and talked about yesterday. We finished with what this is actually saying. It was hard enough just to understand what it's saying. That's how we ended, but we did not prove any of it.
We're doing the proofs.
I mean, I could scroll down to where the auxiliary segments are going to be, but we still have 4 minutes of pre-class time, so.
We have these 3 cases about the secant or something, and then we're stopping to prove.
Start with case 1.
Yeah.
For all of you just joining, we're proving this first case here. Here come the auxiliary segments. You're proving that A times B is equal to C times D. All right, 8:30. Morning.
Yes. My mic's not. Okay, never mind.
Prove that A times B is equal to C times D. Look at the situation. Now this appears to be two chords, but it could be two secants. And what's special about them is what? What are they doing? What is the red chord and the blue chord? What are they doing?
Intersecting.
They're what? They're intersecting where?
Not on the center.
Okay. Not where they're not intersecting. Where are they intersecting?
Inside the circle.
Mm-hmm. Color coding definitely helps. So you got little c, little d, little a, little b. So A times B is supposed to equal C times D. And they draw auxiliary segments. Now you have triangles. So let's get started. This angle here, we'll call this angle 1, 2. Angle 1 and 2 are congruent by the vertical angles theorem, right?
Yeah.
All right, now let's take a look at angle 3 and 4. Are they congruent?
Yes. Yes.
Why would they be congruent?
Are you talking about? Never mind.
The angles intersect the same mark, CB.
These inscribed angles 3 and 4 both intercept arc CB. Take a look. Angle 4, watch it. There. Angle 3, same arc. So if they intercept the same arc, they are congruent. Now, if two angles of one triangle are congruent to two angles of another triangle, what do we know about the triangles?
Similar.
Ah, they are similar. All right. So these triangles are similar by the Aa similarity. Yes.
Aa Similarity Theorem.
Was it theorem or postulate?
We didn't postulate
I
that.
don't remember.
We proved the Aa similarity theorem?
I think we did.
Okay. Well, one of your books postulates it, and another, it might, and the other book theorizes that and proves it through rigid motion, I believe. But that's trivial at this point. Right now, what we need to worry about is now that these are similar, what are you going to do with that? Oh, by the way, this point of intersection is point P.
In like base
You know that
angles.
the other angle is congruent.
Okay, so if you want to make that so that you can keep track of what side corresponds to which side, we can make ratios out of corresponding sides, and those ratios can include A, B, C, and D. All right, so let's start with A. A is corresponding to what in the other triangle? So
B.
hold on, don't
B.
shout it out. You can always put it in the chat. But here, if you look at A, this red part,
Right.
in this triangle, it goes from the 2 to the 1. So we're going to go from the 2 to the 1, the angle marks. So that's going to be D. A is to D.
Yeah.
Okay, now let's go to C. C here has the angle 3 and the angle, the one marked 1, 3 to 1. So C is going to correspond in the other triangle to the 3 to 1, which is the B. Okay, so what's the reason that these ratios are equal, or that the corresponding sides are proportional?
They're similar.
Definition of similarity.
Definition of similar figures.
And then cross multiply.
Okay, so then by the cross products property,
AB equals CD.
is equal to CD. Are there any questions about the proof of the first case?
No.
So with the auxiliary segments, it made it very doable. Without the auxiliary segments, you could have been trying to do that and figuring that this was one of those really difficult proofs. So, I mean, the auxiliary segments are the hardest proofs to remember years later. I'm just giving you from my own experience. When even 1 year later, if I were to come back to this without reviewing it, and I wasn't given those auxiliary segments, I would have trouble trying to do this proof. It wouldn't necessarily occur to me. I could try for a while and it might come to me, what to do. But you could really get stuck on these proofs throughout the year. We've had proofs where they require auxiliary segments, and without remembering that you're supposed to put one there, it doesn't necessarily occur. Sometimes it does occur to you what to draw. So, like what if I were to give you case 2? Would it occur to you in this middle case where to draw an auxiliary segment? Or
No.
would it occur to you that you would
Key
need
to
two
the book.
Now listen, would it ever occur to you that you might need 2 auxiliary segments? And how would you know when you needed 1 or 2?
I would use the WL basically. The left hand point.
Where is there an S?
X.
Z, sorry, that's
No.
Z.
Oh. Yeah, WZ.
And Z is the length here.
I know, but you didn't mark the points, so.
Right, so we'd have to make them. So
I would use the left endpoint of W and the left endpoint of Z. Draw a segment there.
Should I uncover what it is? Here we go. Ready? Where are they going to be? There they are.
Yeah, that's what I thought.
Both. I was going to do the other.
Yeah.
All right, so everybody draw that in your notes. I'm going to do the same. And you go ahead and get a head start on trying to prove. What are we trying to prove again?
VW times VX is equal to VY times
Put it in the chat. I want everybody else to think about what you're trying to prove, because that's how we ended yesterday, is what are we trying to say? If you don't even know what we're trying to say, then how are you going to prove it? There's no way. You're just going to accidentally prove something you don't even know what you're proving. And you're proving the same thing that we just proved, but from a different perspective, because these are 2 secants now meeting not inside anymore. We're not talking about the red auxiliary segments. We're talking about the original black segments here that meet outside the circle. That's what's special about this case from last case. Okay.
First off, can we use the previous case for this one?
Of course we
Yeah,
proved it.
yeah.
We proved it. Circle O again. That's circle O. You here have overlapping triangles. Okay, and that's going to be important. I want you to, okay, let's think about what we had said yesterday. Let's try to remember back to yesterday. So let me do this. We said that a point, whether it's inside or outside the circle, you can draw infinitely many lines through that point. But we don't care about lines that are out here. We care about the lines that are interacting with the circle. So those would be tangent lines or secant lines. Now in the first case, we had a point where these 2 secant lines were meeting inside the circle, right? So we had this point here where 2 lines are meeting inside the circle and at point P. And we had started this whole thing with, here's an A1 and a B1. Remember that? Right? And when you multiply from A1 to P, that distance times B1 to P. That's constant is if you had an A2, this other line along, and remember there's infinite lines that go through point P. So there's an infinite amount of these. And if you have an A2, B2 that, again, it's not what's happening out here, it's how this line is interacting with the circle. But we discovered that that line that you draw is going to interact with the circle in 2 points. Okay, and if it's a tangent line, we'll get to that, it only interacts at 1 point, but you do it twice. Okay, but right now let's go back to where you have secant. So it's going to touch the circle twice. And basically the way you think about it is you go from point P to one of those locations, and that has a value. And then from that point to the other location along the same path, along the same line, there's 2 locations. Those 2 distances get multiplied. And when they do, you get a constant. Okay? Now, if I move that point to over here, a different point W, I'll get a different constant when, and depending, it doesn't matter what lines I cross through here, random lines that cross through, this distance and this distance, when you multiply them, is constant. That's the same as this distance and that distance multiplied. Okay, so that's what we were saying. Now, coming back out, what happens when the point is outside the circle, it doesn't matter. The same thing, the same principle is true. It's just some of the details change because that point is outside the circle. So again, I want you to see it as you're going to pick one of the infinite lines that's going to go through V, right? And here's that line, and we're going to take this first pathway, Vx, right? We're taking this pathway. Along that pathway, there are 2 locations, 2, count them 2, where that line is going to intersect the circle. Here at W, so you're going to have this distance here. And then the second place is over here at X. If you follow that pathway, this problem is difficult for students because of all the overlapping stuff. Okay, so you have the green and you have the blue, which have values. Why do they have values? Because they have lengths. Okay, so blue times green. Blue times green is constant. Any line that you draw through, V that also is a secant or a tangent to the circle, secant or tangent, anything that interacts with that circle along a pathway is going to have the same product of the 2 different measurements. If it's a tangent, then that measurement is the same. Okay, we'll get to that. That's going to be the next case, so we don't have to worry about that right now. That means, let me get 2 other colors here. That means that if I go through V along a different pathway from V to Z, that means this first mark here hits the circle there. That's the first point. There's going to be 2 points it hits the circle. There's the first one. It makes contact along this trajectory with the circle here at Y. But there's another location along the same trajectory coming along here. It's going to hit the circle here at Z. So purple times brown has to give you the same result as blue times green. And that's what we're saying. So the way that I think about it, that's what helps me remember what this is all saying, because it can get very tricky, all right? So what it means is that along the same pathway, 2 points of contact, when you multiply them, you get a constant from any point that you can make. This is a relationship between a point anywhere on a plane and a circle somewhere on the same plane.
I proved it.
Okay, great. Okay, so that means I can take a circle and a point here, a point there, a point there, a point there, a point there. In a plane, all of what we're talking about is the relationship between a circle and a point, right? When you draw a line, let's pick the inner point. Any line, any 2 lines you draw through it, this times this is going to equal this times that. Oops, this. From points outside, then I can draw, let's take this point here. I can draw here to here and here to here. Then this times this, that's going to be harder to see, is, and that's what case we have now, is equal to this times the longer one. Okay? Shorter, longer, multiply them, get the product. That's equal to the shorter here times the longer one here. Okay? And then the third case we're going to get to is, let's take this point out here. Let's say it's tangent there, but secant, through this point out here, you draw a secant, and it touches the circle in 2 points. Then short times long is constant, of course, but it also works with the tangent. It's just the tangent only has 1 point, so it's 1, 2. It's 2 to the same length, 1, 2. So it's squared. So if that's a distance t, then it's just t squared. And then this one, t squared is going to equal the short times the long on the secant. Okay, that's the next case. So there's a circle with all 3 cases in one circle. All right, so I know this gets tricky. You can watch the video later over and over and rewind it so you understand when you're doing the homework. Now, let's prove this case. How do we prove the first case?
Find the overlapping triangles. It's much easier once you find them.
Find, what do you mean find them?
I couldn't see the overlapping triangles.
Oh, you mean separate them?
Oh, there they are.
Yeah, but make sure you see them first.
Okay, let's separate them then. So I have this one on the top.
VWV. And
Hold on, let me label it.
VXY.
Wait. And then the other one I have is this one here. VWV. Okay. And let me try to get some of the colors good for you guys. So I have, this one's blue. I have VY as purple. Okay, not drawn to scale because I'm going to get that these triangles are similar. I hope you understand that. That's going to be the same thing we did last time. We said that the triangles were similar. These definitely, I did not draw them as similar triangles. I'm just trying to get the colors for you guys so you can see where they are in that one. Okay, so.
Angle V is congruent to angle
Hold
V.
on, David. You can put whatever you want in the chat. Put whatever you want in the chat.
David, please don't yell.
David, stop like shouting out. Put it
He
in
can't
the
help
chat.
it. Sometimes he can't help it, but we're going to work together to try to help each other.
By the way, there's no video signal on the slides. Look to you.
Oh, yeah, thanks.
You can't not have noticed.
All right, so the first thing I'm going to do is say that V is congruent to itself by the reflexive property. Now I have one angle, all I need is another angle. Okay? Now, let's go into the circle here. Let's look at
You could have angle Y is congruent to angle W because they both intercept arc XZ, right?
Yeah, and that's fine, you can do it that way. I'm doing, look at these angles 1 and 2 here.
Yeah, I did that too. I just did both of them at the same.
Yeah, you can do that. Okay, 1 and 2 both intercept that little arc there. Okay, so that's this angle here and this angle here. All right, they both intercept the same arc, so therefore they are congruent, and the triangles are similar by the Aa Similarity Postulate. Okay, any questions about that? All right, so I like to mark the third one so that I can make sure my corresponding sides are corresponding. All right, that's helpful for me, those, at least for me it is. All right, so now I want to make some claims. And I want to make claims that give me the blue, the green, the purple, and the brown in a proportion. Okay? So I already have them marked. So let's go with WV. Why not? WV is a 3-to-1. That's why these help me so much. That corresponds to YV.
Mr. Roosevelt, could one draw a line from W to R?
For what?
From W to Y.
From W to Y, yes. Why would you want to do that?
I was just wondering.
Postulate 1-1, through any 2 points, there is exactly one line. Okay, so WV is blue, YV is brown, okay? No, excuse me, purple. And that will be equal to, let's see, so I did blue is to purple as, let's do brown. So ZV, and ZV goes from 2 to 1. So here we're gonna go from 2 to 1. So it's gonna be XV. All right, and then that's the definition of similar figures or similar triangles, okay, is that their corresponding sides are proportional as part of the definition, okay? And then we'll use the cross products property. So we'll say that WV times XV is equal to ZV times YV. And that's just the cross products property. I just cross multiplied, all right? And that's it, you're done with the proof. Now, why did the proof look more complicated? Well, because they labeled these in up above. They actually labeled the values here. They said that from here to here was X, from here to here was W, from here to here was Y, from here to here was Z. So let's examine carefully what this is saying. What is WV? WV is in this orange W to V is this blue, that's just W. So we can write W, okay? Times, what's XV? If you look here, XV, X orange to V orange, that's the green one. The green one is made of this little x and plus the W. And that's equal to, on the other side, ZV, or we can do Y, it doesn't matter which one we do first, YV. YV is here, it's this purple one, it's just Y, times ZV is the big one, which is made out of Z plus Y. And that's why it looks like this. Because you must add these two. Now, yesterday it came up, why not just refer to it this way? This seems easier. But when you do the application, and I give you 3 out of the 4 of these numbers, look, X, W, Y, and Z. If I give you 3 of them, and you're gonna solve for the 4th one, you're doing it this way might make you make a mistake because you have to add X and W together to get the green by itself, and then you have to multiply by W separately. And your brain might say, well, if I add it X, if I already used W, the student that gets this wrong is going to just say W times X is equal to Y times Z. See what I'm saying? Students that make an error are just gonna say W here times X is equal to Y times Z. That's not true. It's this segment times the entire segment.
Y times Y plus Z.
Yes, it has to be this. And that's why this is useful in addition to understanding it this way, to understand it that way. Because when you apply it, you're going to need to add the 2 lengths for one of the factors, and the other factor is just the shorter length. All right, so we went kind of carefully through that. Hopefully you followed along. You can always go back to the video later. You can ask me questions now. Anybody?
Wait, Mr. Rosenthal, where do you find the videos like for these streams? Because
Joshua Rosenthal is my channel on YouTube.
So it's on YouTube.
Yeah,
Finding
all of
out
them,
what
all the
happened.
ones that we've started since the beginning, since that very first Monday that we were home, every single one of them's there.
If you
The first couple ones are in live. They were done live before we went to Zoom, like the first 2 of them, I think. And then after that, they're all in the other videos, the regular videos. All right, no more questions here? Then let's go to the 3rd case. Let's see if you can come up while I'm erasing. Can you come up with the auxiliary segment or segments that you're going to need for the 3rd case? start drawing this. Look at what you're trying to prove. From that point to T twice. You multiply it times itself. Should be equal to this distance y times the entire distance, which is y plus z. Okay, and we have to prove that, and it's going to be done similarly, pun intended. It's going to be done similarly to that of the last one.
Wow.
That's what I always say. Wow. All right, so let's see if you want more time to see if you can come up with the auxiliary segments yourself before I give it away. If I don't hear a yes, I'm just going to go to the show you.
I want to figure it out.
You want to figure it out?
Yeah.
Okay, I'll just show you the auxiliary segments from the last one.
Okay.
Now all you have to do is bump this up and it becomes tangent. Do you think that they're gonna?
Oh, I get it. Okay.
Remember what you're trying to do in case 1 and 2, you got similar triangles. You need to find a way to get similar triangles. Not only that, you get them similar by having inscribed angles sharing an arc. So that's what you're trying to manipulate geometrically. Usually we're used to manipulating equations in algebra. Now we're manipulating geometric figures and auxiliary segments. We're manipulating that. It's interesting to think about it that way. We're manipulating geometry so that we can prove something is true. And that's really doing geometry.
Can you draw the figure without the auxiliary segments?
Here they come. Here it comes.
I think I got it.
Ah.
I knew it.
Okay, so this might be tricky to see.
Construct Texas and TY.
But what was our strategy for being able to see the overlapping triangle problem? The trick that we've used all year since we learned about overlapping triangles was separation. It really can help you. Okay, start proving it. Here they don't even try to draw a center.
Does the inscribed angle rule still applies to angles such
yeah.
as V, right?
Yeah, the tan.
Well, we had a theorem, right? The theorem said when a chord and a tangent intersect and they form this arc, then this is the same as the inscribed angle here that has that same arc. So this angle here between the red dotted line and TV, that angle there is the same as this angle here, right?
It's half the.
Because they're both half of the arc. All right. So let's try to get these similar triangles split. So I'm going to have my small triangle here. T, B, Y. Try to draw it like that so you can see, oh, it just came right from there. The trick here is in trying to get your brain to get rid of all that extra stuff that's, that's all in your way of seeing the problem. Then you have the big triangle here. T, V. I tried to draw it more like that now. Okay, and then maybe that's a little bit longer than I had. Something like that. Doesn't matter. Bob Ross. Doesn't matter.
Not mistakes, just happy little accidents, Mr. Rosenthal.
Yes, thank you. I don't feel alone in the world. Happy little accident. That's great. You made me laugh. Not hard to do. I need a brush so I can go ba 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 ba.
Beat the devil out of
Beat the devil out of it. That's right.
Happy little trees, happy little trees, happy little trees.
Yeah. Bravery test. All right. Again, angle V is congruent to itself, right? So I'm going to mark that angle. As, okay. And then you have this angle up here. We can call that angle 1 if you like. Doesn't matter. Oh my God, I started a whole thing. All right, so angle 1 and 2 are congruent because they both share the same arc. So I hope everybody sees that. So that angle there.
Would have thought that.
Nope. All right, so now these triangles are similar by the Aa Similarity Postulate. And we're going to mark the third one so that it makes it easy to set up a proportion. Hopefully that is true for you guys. I hate to think that, oh, I keep saying this makes it easy, and you're thinking, no, not really. I'm still having trouble doing. I'd hope you'd speak up. But the markings, if you don't understand what I'm doing, say so, and I'll try to explain what I'm doing here when I make my proportion.
The 3 markings are unnecessary. You can just do 1 to none instead of 1 to 3.
Can, yes, you can. All right. Now, let's see. What do we want to say? We want to say that from any point outside or inside, there's some pathway you can follow that's going to interact with the circle. Either they could be a secant or it can be a tangent. We don't care about the ones that don't interact with the circle. We're only talking about the ones that do. So we've already done when there's 2 secants meeting inside, 2 secants meeting outside at a point V. And now how about why don't they have a tangent and a tangent?
Because that wouldn't work.
It would work. If you had VT and then the VU.
Oh yeah, it would be the tangent squared equals the tangent squared, but the tangents are already congruent.
They're already congruent. They're already congruent. So you don't need a tangent and a tangent. We already know that the 2 tangents are going to be congruent.
You'd have x squared equals x squared. Yay!
Yeah, it's an identity. All right.
Mr. Rosenthal, could you repeat that?
Why do we only have 3 cases? What about a tangent and a tangent? Why did we have a secant and a secant meeting inside, a secant and a secant meeting outside, a secant and a tangent meeting right now outside? See, the tangent and the secant are meeting outside the circle. Why not a tangent and a tangent? Because you already know that those are the congruent distances, right? So if you're trying to say that we already know that those are congruent, try setting this up. If this distance is x, and you have another distance that's v to u is also x, then what you're going to get is x 2 times, but not 2x, but it's x times x, is going to be equal to x times x. You're going to get x squared equals x squared. You're going to get an identity. It's not going to help you to solve anything. Okay, so this gives us this last case. And what we want to do is we want to get VT and we want to get VY. That's that first point of contact along this trajectory. Y would be the first point of contact. So we need to get that in there. And then the second point of contact along this trajectory is VX, is the X point. Okay, so we need to get VY, VX, and VT. All right, so let's start with VY.
Just so you know, Mr. Rosenthal, there's a way you can share your screen on whiteboard mode.
Yes, but if I share my screen, then you're not looking at me on a board, right? You're looking at whatever I'm doing on some virtual board.
Okay.
We've been over this. Okay, so I'm saying I need VY, so I look at my 2 separated things. I don't have a VY here. The VY is only a part of the smaller triangle. VY is a 1 to 3. So I'm going to go, so 1 to 3 is not here and here, it's here and here. So it's VT. VY is to VT as, okay, now let me get that longer segment, VX. As VX, Okay. So, oh no, wait.
Oh, you did the wrong one.
No. Hold on. Can't do that.
You have to start with the small.
Yeah, because VY is part of the small triangle. So I did a small to large. So now I got to come back to this one here, the small one again. And I guess I'm going to do VT. I'm not going to use the auxiliary segment because we're not trying to prove anything about the auxiliary segments. So VT is 2. So VT here is 1 to 2. VT here is not 1 to 2. This VT here is 1 to 3. 1 to 2 here is that VX. Okay, why? What's the reason? Put it in the chat. What's the reason why is this proportion true? Nah, in the chat. Nigel's got it. I don't know how many subscribers I have. You'll have to go to the site.
I think you've got like 20 or so.
To find his channel, though, you have to put math after the name.
I just searched it, Joshua Rosenthal, and there might be a couple others. I don't know, but that one, you don't have to look very far. There's not a lot of Joshua Rosenthal channels. So, all right, so here we go. This is true because the triangles are similar. So this is definition of similar figures or similar triangles. Okay, cross product. Vy times Vx is equal to Vt times Vt, or Vt squared. And if we examine what that says, Vy is this piece, right? Along that trajectory, times Vx is also along this trajectory. It's the long piece. So blue times red makes purple.
Mr. Rosenthal, isn't there an easier method to approach this geometric mean? Because if you know that, then you could just say that Vt equals square root of Vy times Vx, which means Vt squared equals Vy Vx.
Vt squared equals Vy times Vx.
Yeah, geometric mean.
If you want to word it that way, you can say that the tangent segment is the geometric mean between these two distances, the blue and the red. Vt is the geometric mean. Purple is the geometric mean of blue and red. Yes, you can say purple is the geometric mean of blue and red. That is something you can say because we've proved it.
You actually have 176 subscribers.
Nice.
Wow.
Any questions about this? Because now we're going to go and do the application. The application is more fun. The mistakes that are going to get made in the next couple minutes here are going to be the mistakes I said. It's going to be that students, when this is X and that's Y and that's T, let's try to get that in there. If we label this X and that Y and this T, what students do is they do T squared is equal to X times Y. That's the mistake they make.
Yeah.
And that's wrong. It's X times what? Red is made out of X plus Y. Yeah, and you're going to get quadratics sometimes doing this.
X squared plus XY.
Right? You're going to get quadratics when you do this. So you're going to have to go back to your algebra again and solve quadratic equations. Any questions? Let's apply it. Let's go. You got through the hard part. Now the application is the easy part. Go ahead and find the value. This is a Y. And over here, that's a Z. Find the value of Z. And this is what the problems look like. I wonder how you're setting that up. 10 more seconds. I'm just going to set it up if you haven't set it up already.
I think I know the answer to the first one.
Okay.
Yeah.
Let's put it in the chat then. Can you explain again how you got the triangles to be similar? Ooh, too late on that one. You're going to have to watch the video. What I did is, okay, if I could explain to you, you can look at your notes. The V angle was congruent to itself by the reflexive property. But in that last one, you had a chord and the tangent forming an angle, which was half the measure of the intercepted arc. But then you also had that other angle, the far angle, which was also an inscribed angle with the same arc. So that's how I got that second angle, is because the two angles intercepted the same arc on the circle. So that's how I got that second angle. And once you have two angles, the triangles are similar. Okay, answers are starting to come in. Okay, good. Got it. All right, here we go. Setup for this one. Incorrect setup would be 6 times 8 equals 7 times y. Wrong. Or some students that are a little bit further along that make a mistake might say it's 8 times 8 plus 6. No, that's why I try to help you with remembering from the point to the circle twice. Okay, think of a relay race. The first step is to run the 6 and back. Oh no, just run the 6. Then you got to start over and run the 8. Okay, all right. So not the 8, excuse me, the 6 plus the 8. I just did the same thing. Okay, so it's 6 is that first distance. The second distance is 6 plus 8. And that's equal, along the other trajectory, to the 7 times the 7 plus y. Okay, now you can see the problem becomes a quadratic when you switch the variable to out here. And you put the number in here. Put the constant inside and the variable outside, and what's going to happen is you're going to get a y squared.
Y squared plus 7y plus.
We gave you the easier case. Okay, so 14 times 6 is 84. This is 49 plus 7y. We subtract 49.
In the second problem, we were so close to a perfect square.
Sorry,
Why did you do that to us?
I didn't.
Uh-huh.
Okay, this one is 35. And then divide by 7y is 5. And you can try it. Plug the 5 in. So this is 6 times 14. And then this one would be 7 times 12. They're both 84.
Yeah.
It's that adding the two that gets people. This is one I had put an asterisk by for the test. A lot of these get missed for no reason. I mean, really not. It's just you're not studying it enough and practicing and being aware when it happens on the test. Okay, any questions about red? Then we're going to do blue. Once it's not a smart board, so I can't hit the back button. Too late.
Dumb board.
Took too long. Okay, here we go. This one.
Joseph, it's rude to call people dumb.
Oh.
Yes,
Opposite of
it's
smart.
definitely rude.
It's a moderate intelligence board.
No.
The complete
IQ
non-intelligent
board.
Okay, here we go. Z squared is equal to
IQ
8
isn't an actual measure of intelligence.
times 8 plus 16.
No,
Or
it's
is it?
not.
It is. Wait, no.
Z squared
Well,
is
it
equal to 8
depends.
times, you guys are having a conversation here, huh?
Yeah, it depends on what you're measuring.
162. Okay, square root both sides. So that's 296, 248. That's 16 and 3.
3.
Okay, so I have the square root of, so I have a 2. I have the square root of 16 is 4, and I have that, so I have an 8 root 3. This is going to come in just a second. The same square root of 192, remember that. It's going to come out to that. That's going to come into a problem very shortly now. I just realized that now because I had done the problem already.
It's not a perfect square.
No, but this is Z. Any questions? 8 rad 3.
You could have made it 4 higher and just made it come out to a perfect 14.
Coulda, shoulda, woulda. Didn't. Any questions about this process? This is what it looks like on the test. Did you say that the segment outside the circle times the same segment inside the circle is equal to the other two segments? No. No. What we are saying is that, I don't know if you mean this problem or the last problem. What we were saying is that from that point, that distance z times that distance z again is equal to the distance of 8 times the distance of 8 plus 16, all the way to the second point. So traveling from here, the long path is 8 plus 16. Okay? From here to the first point of contact with the circle, it's just 8. That's why you see this. That product is equal to that times itself. Okay? Oh, I know now. Thanks for clarifying. Okay, you got it. Who's benzo?
I think it's the name.
Probably Enzo.
Probably Enzo or Ben. I think it's Enzo.
Yeah, but Enzo,
The
no,
UPO fusion
Enzo,
card.
you're
Somebody
changing your
Ross.
name. You already came in as Enzo. Okay.
Wanted to be Bob Ross.
You guys must be bored if you're while you're doing geometry, you're taking the time to change your name. All right, here we go. Here's one of those fun problems. This is the arch of the Taiko Bashi.
Oh.
It's an arc of a circle. Okay, and here we go.
No, I can't see.
You can't see it?
There's a glare.
What about this part? The glare is in the picture. That's the way the photo was taken.
No, you can't see the text.
Yeah, the glare is on the text.
Oh yeah. I'm reading you the text. That's the Taiko Bashi Bridge.
We also
Right.
can't see the diagram.
Okay, hold on. Let me read it to you. A 14-foot chord is 4.9 feet from the edge of the circle. So if you were to draw a chord here of a circle, right? And it was split, but it was 14 across, right? And here's a diameter splitting it, and it's perpendicular. So you can make your conclusions from that. This distance from the chord to the edge of the circle is 4.9 feet. Find the radius of the circle. And I'm going to draw it here so that you can get a better look at it. So the chord is 14 across, but the intersection of this diameter and the chord, it's perpendicular, but from that intersection point, the distance is 4.9 to the edge of the circle. Find the radius of the circle. And I like this problem. Good for you, Mr. Rosenthal. We're happy for you.
Yoo-hoo.
We would say that, but
I already did.
okay, that's not.
That's a diameter, perpendicular to a chord. You might think of this as the ground, maybe, something like that. Okay, then this distance, because it's perpendicular, then it bisects the chord, if you remember that. That's 7 and that's 7. And then this is 4.9. What's the radius is what I'm asking for. I'll give you maybe a minute and a half. Go. And of course, you should be using what we just learned.
Okay, is there something on the
7.45?
arc?
Two chords intersecting inside of a circle.
Yes, I think you're
7.45?
right. Yes, 7.4.
Wait. If you have an answer, you put it in the
I
chat.
don't. Yeah.
Oh, sorry about that.
That is okay.
No, it is an unforgivable crime. You must be punished.
In which case you're an outlaw, Dave.
I'm not an outlaw. I didn't spit on the street in Singapore.
All right, relax. Hold your comments right now, people.
Oh, don't worry. Singapore, they arrest you immediately.
All right, that'll be enough. That'll be all.
You're
That'll be all. Mute yourself. All right, so if there's a point, then the distance to the circle here times the distance to the circle the other way along the same trajectory is constant. So that's equal to 7 times 7. And the numbers are nice for you. So 4.9x is equal to 49.
I
Divide,
wonder what 4.49 divided by 4.9 is.
okay, x is equal to 10. But that's not the answer, because if this is 10, that's not the radius. So what you do is you then think, oh, then what is the diameter? The diameter is 10 plus 4.9. So then the radius is half of that. And our units are feet. All right. So we've gathered from a partial circle, like an arc of a circle, you can find the radius of the circle, even though you don't have the complete circle. All right, because of what we just learned. All right, so the engineering applications are wonderful to that, because then you can build partial arcs of objects that you don't need the full circle, and you can make those calculations no problem with simple mathematics.
Can you go over one more time how you got 14.9 after you got x is 10?
If this is a diameter, this whole thing, and this part is 10, and this part is given as 4.9, add those two together.
Oh, so that's the diameter. I thought that was a chord.
Well, a diameter is a chord, but yes, this is the diameter. It goes through the center.
Okay, and the radius is half of that. That makes sense.
That's right. Any other questions? No? Okay. I have another problem for you. This one is also good. All right, this is automotive engineering. This is called a Wankel engine. So I'll just show you the picture of that.
Oh, are we gonna learn stuff about the
Rotaries, baby.
differentiator?
Oh, some of you've already seen these types.
Yeah.
Yes.
I'm a Mazda fan, my guy.
I've 3D printed
I love
that.
Mazda.
That's right, the Mazda, exactly. The
RX-7.
RX-7, yes, exactly.
Yeah.
Yes, the triangular shape. It's a very strange.
Donut engine. The
Spin
burrito
it.
engine.
It was a very high.
How'd you know that?
Under the car fanatic.
I have a car obsession.
I love the
Car
RX-7.
enthusiast.
It's one of my
What's
favorite
the
cars.
point of knowing these things about cards? There's no real
Yeah.
value to the.
David, let me answer that. Everybody quiet, please. So somebody might say, what was the point a long time ago of the NASA space program? Anybody who's been watching Neil deGrasse Tyson over the last several years would hear what he was saying about all of the other technologies that were indirectly discovered from the NASA, all the work that they did with NASA. So by studying certain things where you think, well, I'm not that interested in that, the things that you learn from that give you ideas for other things. See what I mean? So that's
It's not the non-interest. It's just that it's the futile, or it's the pointlessness of memorizing the fact that exact model of car has that exact engine shape, and that's exactly what it
Multiple
looks
cars
like.
with that in.
Also, how
But,
is
I
this gonna
mean,
help me
who-
cure cancer or
Who
something?
cares?
it's
Doesn't
an
matter.
experience.
It's the reason why I memorize all this stuff and like know all this stuff, like the models of the cars, what engines they have, is because I like doing that. It's just fun sometimes.
Yeah,
Just
that's like
that stuff.
Oh,
That's all
in
you
that
do.
in that case, it's understandable.
Well, why'd you learn to solve a Rubik's Cube? It's not going to help you cure cancer.
It's
called a hot.
If it's fun for you, then it's understandable.
All right, that's a good conversation. Let's have that later because we want to finish this lesson now. We have 5 minutes. Not that we're in a rush. I just don't want to chop it into pieces where this is the last thing. So I want to just finish the thoughts here. Last application. Okay, so this Wankel engine has this equilateral triangle that's part of the engine. Each side of the triangle is a chord you could think of an imaginary arc that you can make with each of these chords. So that does not form a complete circle, right? Obviously, this is not a circle, right? But you can imagine that there is, along this blue arc, that there is some circle that comes around this center, right? And I have that on the next page. I'll show it to you, all right? So the opposite vertex of the triangle is the center of the arc. If you want to think of where would the center of this circle be if there was a circle here, if this completed the circle out here, that would be the center, right? And this would be the center of a circle done this way. And this would be the center of a circle done that way. And you'd have three overlapping circles, okay? So that's the design of that engine is follows that. So in the diagram, each side of the equilateral triangle is 8 inches long, all right? So I want you to use what you know about equilateral triangles. Don't use anything that we've just been doing. Just take this as an equilateral triangle problem. Think of your ratios that we've talked about. And I want you to find the value of x that way and don't move on to the second part of this. Okay, so find the value of x just using what you know about equilateral triangles. And I'm going to try to draw this now. Made that a little wide. That's x. That's split evenly. This whole thing is 8. This is the center of some imaginary circle. Doesn't matter in this case because we're just going to treat it as an equilateral triangle. Okay, you can put your answer in the chat. We're going to go slightly over time here just to discuss the rest of this problem. Just a few minutes. Doesn't matter.
Doesn't matter.
Is that the new thing instead of what I thought that?
Maybe. Okay, let's see. So I'm going to make this 4. And I'm going to draw this out to here. And I'm going to say that if this was 60, 60, 30 right angle, then I know this distance here. What is it?
8.
4
Oh,
right.
4/3, right.
How do you know that it's a 30, 60, 90?
Because it was an equilateral triangle, so it's equilateral,
Oh.
and then you split it, right? That was our proof for our ratio.
Yeah.
Right? That's how we proved that the ratio was whatever that is times √3.
I got X.
Okay. You are not doing
Good
anything
news.
with, hold on, you're not doing anything with 2 chords meeting in a circle right now.
Oh no.
What you're doing is that if this is a radius to the circle, and that's 8, and that's 8, and this whole thing is a radius to the circle, then that whole thing is 8.
Ah.
So x plus the 4 rad 3 has to be the radius of the circle, which is 8. Right?
Ah.
So x is just 8 minus 4 rad 3. Done. Now I'm going to erase
Oh, that was
this.
simple.
I'm going to erase this. All right. So you should have this in your notes, and we're going to compare it to doing it a different way. Now we're going to tie it in, and then we'll be done for the day. So we're going to go a few minutes over. I want you to copy the diagram and complete the circle with the given center. Then use theorem 1212 instead to find the value of x. Show that your
Already did.
answers to part A and B are equal. So it's going to look like this. Now imagine that circle. Okay. And you're trying to get 8 minus 4 rad 3 is what you're trying to get.
Mr. Rosenthal, we can still use the result from before, right? That the central line, the vertex angle bisector of the triangle is 4 rad 3. We can use that.
I want you to use 2 intersecting chords.
Yes, that's what I mean. I was just asking if we could still use 4 rad 3 as the line
long as
through
you're
the triangle.
Yes, as long as you're using 12, 12.
Oh, then it would be extremely easy.
You think so, huh?
Extremely.
Yeah, so all you have to do is do x plus 4 rad 3 equals, no, x times 4 rad 3 equals 16.
Okay, at this point, I'm going to try to catch up to you now. This is 8. Okay. You can say that this is, no, but now then you're using the equilateral triangle. Well, I guess you can use the equal, but let's say you weren't using anything about the equilateral triangle. Okay, what would this distance be then? It would be 8 minus x, right?
Yes.
Yeah, that's what I'm saying.
This
Yeah.
whole thing is 8 because it's a radius. That whole thing is 8. That's 8. That's 8. They're all radii. So this distance here is 8 minus x. All right. All right. So now let's just do the problem because we're over time. 4 times 4 is one side because they're intersecting at that point. So the distance that way times the distance that way is constant. That means x over here, this piece here, is going to get multiplied to this entire thing. That's 8 plus
Oh,
8 plus 8 minus x. Okay, so 16 is equal to x times 16 minus x. 16 is equal to 16x minus x squared. I'm going to add everything to one side to get positive x squared over here, minus 16x, positive 16 equals 0. Let's put it in the quadratic formula. X is going to equal negative b plus or minus the square root of b squared minus 4ac all over 2a. And let's see what this simplifies into. Positive 16 plus or minus the square root of 256 minus 64. Guess what that is? Square root of 192, which is what I told you to remember. Okay, so square root of 192 gave us what? 8 rad 3?
Hey, it's not 64, it's 32.
What?
2 AC. 2 times 1 times 16. 2 AC.
It's 4 AC.
4 AC.
David, it's
It's, you get this. Okay, the 2 now, you get 8 plus or minus 4 rad 3. Okay, so one of the answers is 8 plus 4 rad 3. The other answer is 8 minus 4 rad 3. This is that's the one we got in the original case, remember? That was our, doing this as an equilateral triangle, we got this one. What's that one?
Extraneous.
No, it's not. Although it cannot be x, but what it is it's this entire distance here. This is the other unknown piece, right?
Oh, as in the diameter, not minus x.
Remember, this is 8 plus 4 rad 3. That's what this piece is. Remember, we weren't going to use the 4 rad 3 from what we learned about the equilateral triangle. We weren't going to use that. But we already knew that this piece was 4 rad 3. So this 8 plus 4 rad 3 is this unknown piece. That unknown piece we called 16 minus x. So that was the answer to that unknown piece. And this was the other unknown piece. So x was the one we wanted. It's the 8 minus 4 rad 3. And that does it. Okay, and let me just put up the homework. There's 2 different assignments there. And you are dismissed. We are in office hours. Excellent job, everybody.
We can't see
Okay.
it.
what's
Bye.
the homework?
There is no homework.
Please no.
All right, let me pick it up.
No. No. Oh my God.
Whoa,
Aha.
anger issues. Okay, I'm going to write it down myself on my little board. so I can put it in. Page 566, 2 through 24 even.
My luck to run out of graph paper.
Thank you, Mr. Rosenthal.
Bye.
Thank you, Mr. Rosenthal. Actually,
Mr.
before
Rosenthal, I have a
leave-
question for you.
You got it. By the way, this is 12 problems and that's 8 problems, so it's 20 problems altogether.
Mr. Rosenthal, my sister has a scoring system for a school that they implemented like yesterday. And it's essentially like the grade you had before you left for this quarantine
Yep.
will be the grade that you stay with, and you can't go below it, but you can go above it if you turn in assignments.
Yeah, that's already implemented. Mr. Letcher said it on like a
Oh,
thing.
did he? So that's what we're doing now?
For
You
this
can't-
semester, yeah.
I wish for
Okay.
like one grading period.
But does that mean? But we're not going back to school this year.
Yeah, no.
So
That's
does that
official.
mean that the only way we can get a higher grade is by turning in our homework?
Well,
and
I
doing
mean,
assignments.
that's the tricky question, isn't it? It's like I could always just say, well, by taking these tests and improving your grade, you have nothing to lose, right? It's
No,
all-
but I'm asking because like I like in case I wanted to know how to improve my grade, do I have to be worried about getting a bad grade on an assignment because I'm turning in like 20 assignments, like extra credit and stuff like that?
well,
Not
bad.
extra credit, but in general.
Okay, well, think about it this way: a bad grade cannot lower your letter grade. It can prevent you from getting a higher letter grade. Students that already locked in an A are already guaranteed an A.
Oh, okay. But if during the break we turn in assignments, can that grade that we get during the break go down?
What break? The spring break?
Let's say we went into the quarantine with an A, right? But then we came in with a B, for example, and then we came to an A during quarantine. Does that mean that we can go back to a B if we don't turn in assignments?
Yes, I can go as low as what your grade was March 13th.
March 13th.
Okay, so then that's helpful. Thank you, Mr. Rosenthal.
Your 10-week progress report.
And how do we check what our grade was back then? Because now that our grade's updated, I'm not sure what my old grade
The
is.
10-week progress report.
Okay.
You can
when
look on
does that
Schoology.
does
You
that
go
come
to
in the
past
mail?
grades.
Okay, thank you.
Mm-hmm.
Have a great
Hey,
day, Mr. Rosenthal.
You too. That's going to get gamed. It's not, I don't agree with it, by the way, just so you guys know. It takes away a lot of my leverage to get students to, now for the students that are doing this because they want to learn, they want to be prepared for the next level, we would hope that would be everybody, but we know realistically that's not the case. There are students that are gaming it a lot. There's a big chunk percentage of students. I would say the majority are not doing that, so that's good.
I mean, if I'm being honest, I am kind of more relieved than I was before that I don't have to turn in every assignment, because now I have time to focus on other assignments that I know are very important, and I can take like an extra day to do one assignment without worrying that it's going to ruin my grade. Yeah,
I mean, it's not going to ruin your grade, but you're not going to learn as much as we intended you to learn.
And that's true. That's true.
Remember where you're at. You have a lot more years of grade school ahead of you in college. And by not preparing yourself the way we think that you should be prepared, the Science Academy level, you're going to accelerate again next year, right? You're going to do 2 levels of math in 1 year. So you're going to accelerate ahead a year again. And by, that's just math.
Fortunately, we know.
Yeah, and that's just math. So, and you're also going to have a slew of AP courses, and you'll still have to take those AP exams, and it's going to be very burdensome if you are not prepared. And everything you're given is intentional to prepare you. So every assignment you say, I don't need to because of the grade, that is one piece of information that is not going to be in your brain that was in the brains of last year's students. So competitively, you may not do as well as the students of last year. And that's by choice, by choosing to not do assignments.
Mr. Rosenthal, do you know how big the waiting list is for the 9th grade? Because I know most of the kids are leaving.
No, and you know most of the kids. So you did a survey and
No, but a lot of the kids I know are leaving.
More than 50%, you already know that?
That might be a statistical anomaly. You could be friends with more kids who just tend to leave.
there's a group of students that leave that have left already before. That wasn't more than 50. That wasn't 50%. So I don't know how anybody would know unless they took a survey of who was leaving.
Yeah. Although the school population is increasing by any statistical count.
Yeah, and also we are taking in other kids, you know, that haven't necessarily been in the academy, so we could do that too. So there are students applying that have not been to Science Academy.
All right, before I leave, final note is that the Mazda RX-8 was actually the final commercial car in production to use the Wankel engine, the triangle one.
Great.
Thank you, Mr. Rosenthal. Have a good day.
Thank
See you tomorrow.
Goodbye, Mr.
Thank you. All right.
Bye.
Bye. We can't see the homework. Yes, you can. Anybody else? You're staying in here, I'm wondering. Nate, are you here? I'm wondering if you're just leaving your computer on during the lesson. Can you message me to show me that you're here? You can't see the homework? It's been up there for a while. Andrew, Shy, and the other Andrew. I have two Andrews in here. Do you have any questions for me? No? Oh, yeah, me too. Yeah. All right, I'm going to go ahead and end the meeting then. Have a good one. I'll see you all tomorrow.